Thanks everybody for attending this presentation. So I am Daniele Ciani from the National Research Council of Italy, Institute of Marine Sciences. And for today's quiz talk, I will speak about the retrieval of sea surface temperature gradients in the context of a future satellite mission developed by the European Space Agency. It's the 10th Earth Explorer under the name of Harmony, and we will just present some preliminary studies about the retrieval of SST gradient from space within this mission. I really would like to thank the co-authors of this work, which are mainly colleagues from CNR, from the European Space Agency, STEC, and also University of Delft and University of South Carolina. So I start this talk with this very brief introduction on very brief outlook of the Earth observation missions developed by the European Space Agency. From this slide, you mainly recognize three main branches in which missions are developed. And the Harmony mission lies in the science section. Generally, all those missions that are mostly driven by technological advances and the necessity to observe processes occurring at the Earth's surface for the first time. As you can see, emphasized by this red circle, I hope you can see my pointer. The Harmony mission is planned roughly for the year 2030 at the moment. The Harmony mission objectives are very briefly summarized here. So they will be related to cryosphere, solid Earth, and for today's topic, mostly ocean and air-sea interaction. On your right, you can have a sketch of the Harmony mission. It is actually given by two small platforms, Harmony A and B, that would fly in configuration with the Sentinel-1 satellite. The mission is really interesting because it will provide simultaneous observations of quantities like sea surface roughness, wind stress, surface currents, direct measurements of surface currents, sea surface temperature, and also quantities information related to clouds. So the main payloads of this mission are a primary one, which is a synthetic aperture radar, and a secondary payload, which is the topic of today's presentation, which is a thermal infrared radiometer. The mission, as I said previously, is very interesting and has this specific capacity to provide simultaneous observations of quantities related to surface stress and surface thermal features, combining information from the two payloads. And this is very useful for climate studies because it will enable to better understand and parameterize all processes that do regulate air-sea interaction and that have a clear signature in both quantities that can be observed via radar observable and via thermal infrared payloads. You can have a very simple example in this image where in colors we are in the Atlantic Ocean in correspondence of the Gulf Stream, where you can recognize lots of mesoscale and submesoscale activity. In colors you see sea surface temperature, and in black and white with a progressively increasing transparency you can see sea surface roughness. You see that there is a very striking correspondence between roughness at the sea surface given by a SAR and also thermal features. But unfortunately today these quantities are only observed without simultaneity because they are obtained acquiring observation from different platforms. In this case, the Sentinel-1 and the Sentinel-3 dataset. While for Harmony, we will have simultaneity. So with colleagues in my institutions and other colleagues you saw mentioned in the introduction, we have been working on the thermal infrared payload that will embark 4 channels, TIR 1 and 2, a channel dedicated to cloud detection, and a panchromatic channel, a broadband channel in the 8 to 12 micrometer range. The spatial sampling distance for 3 of the 4 channels will be around 1 kilometer, while it goes down to 300 meters for the panchromatic one. The noise equivalent delta T is relatively high compared to state-of-the-art infrared sensors, like, for instance, SLSTR. We will have more details later on this. And it is around 0.15 Kelvin. Here you also have a more schematic snapshot of the Harmony configuration that just enables to see that we will have different views for every each of the two platforms. 5 views for each platform. Everyone giving observations on areas of about 250 by 250 kilometers. So we have been working on 2 parallel activities. One, which is still ongoing, is the SST retrieval algorithm from the Harmony thermal infrared radiometer through split window or optimal estimation algorithm. But for today's talk, we will speak about our strategy to optimize the sea surface temperature gradients retrieval from the Harmony TOA payload. And to perform this exercise, we have been mostly taking into account existing data of sea surface temperature or brightness temperature. We have used some numerical modeling based on radiative transfer models, and we also performed some simplified analytical studies to assess the optimization of the SST gradient computation. So going into a bit more detail, our proposal is to represent the thermal features, so the gradients in sea surface temperature from single channel top of atmosphere brightness temperature obtained with the Harmony panchromatic channel, the one in the 8 to 12 micrometer range. So the assumptions behind this are that in cloud-free conditions, the atmosphere is supposed to create a disturbance which still enables to capture the features given by oceanographic activity at the sea surface, even at the top of atmosphere level. And that this approach can be particularly advantageous if we consider issues like Coregistration that can potentially degrade the information when we try to retrieve SST and in turn SST gradients through a standard algorithm. Our tools of investigations, as also mentioned previously, are for the moment existing data, sea surface temperature and brightness temperature data, in particular from the Sentinel-3 SLSTR sensor and Meteosat Severi sensor. RTM models, in particular we relied on the atmospheric radiative transfer model and also analytical studies. So in the next slide, we will try to illustrate a bit the issues related to co-registration, which is one of the things we want to minimize with our approach. So if we imagine a standard SST retrieval, for instance, based on a split window algorithm, as shown by the equation top right, so we imagine that the SST is proportional to the difference between brightness temperature acquired at different IR channels. If we assume perfect channel co-registration, we have a condition which is well represented by the scheme on your left. While if we have a co-registration issue between the two channels, we may generate an offset in the geolocation of the scene at 2 different channels. And this can generate offsets that can degrade the SST retrieval and in turn the SST gradient retrieval. This has been quantified in a very simple exercise, which is summarized by these 6 figures here on your right. So in panel A, you see a very simplified SST field, which is given as an input to a radiative transfer model. A step-like SST configuration with 2 distinct areas generating a gradient of about 1 Kelvin per pixel in the frontal area. In panel B, you can see the retrieved SST according to a given atmospheric profile. For this exercise, we chose a tropical profile, but any other profile can be chosen and yield similar results in terms of structures. And interestingly, in what you can see in panel C is what happens when we introduce artificially a shift, a zonal shift between the, let's say, geolocation of brightness temperature acquired at the two different channels. When we retrieve the SST with this new configuration, we see appearing spurious features in the right side of this area with a lower temperature, which was not prescribed as boundary condition and which is not found in the ideal case. At the same time, you can see the effect on the SST gradient. You can see that in panel F, the intensity of the SST gradient is somehow smoother and generates the appearance of spurious features which are not found when we don't have coregistration. So in this sense, using information from a single channel can help to get rid of this type of effects. We go on with some other analysis, this time based on existing data from the Sentinel-3 SLSTR sensor. We chose a scene that you see here on your left on September 2020, an oceanographic configuration which is a dipole evolving in the North Pacific, where at the same time you find mesoscale to submesoscale features generating very sharp gradients. From this image, which is actually given by a GHRSST level 2P dataset, we extracted sea surface temperature and also brightness temperature from the S9 channel, which is the one centered at roughly 12 micrometers. For this exercise, we assume the BTS9 channel to be a proxy for our future Harmony panchromatic channel. Although this is a narrow band channel, we assume the proximity with the panchromatic one, mostly due to the expected atmospheric disturbances, being the 12 micrometer more affected due to water vapor. And we compare the thermal gradient description from the SST and the brightness temperature derived gradients. So here are the results. On your left, you can see the very nicely the description of the main thermal features given by the SST field. Here in particular, we are seeing the SST gradient intensity. On the right, you can see the same analysis performed starting from brightness temperature observations. So visually, the thermal features are correctly located, even in the brightness temperature field, although we saw a smoothing effect in the brightness temperature derived estimates by about 0.2 Kelvin per pixel in correspondence of the sharpest gradients. By the way, if we compare these two quantities in a normalized way, so dividing each of the two estimates by the maximum value, we obtain a 2D map, which is basically given by zero values everywhere. We can just see small scale noise, but there is really no possibility to recognize the largest, the main SST gradient features from this difference, which means that the two estimates are able to correctly locate the thermal gradients at the sea surface, so that we have a chance to make a correct description of the structures from brightness temperature field. But this time with Sentinel-3 data, we only had the chance to take a look at a narrow band channel. That's why we went even further, this time relying on another example based on the Siveri sensor on board a Meteosat. So in this case, we used level 1.5 observations from the Siveri sensor. And in particular, we assumed that a given combination of infrared channels from the Siveri sensor is a good approximation of the Harmony panchromatic channel. And we then estimate brightness temperature from the top of atmosphere radiances given in the different channel, and we compared this brightness temperature after computing the gradient intensity for features that are associated to oceanographic activity with the same gradient intensity obtained with our synthetic panchromatic channel. So to understand a bit more clearly our strategy here, I present the spectral response function of the infrared channel from the Severi sensors, which are the ones given in colors. In particular, the ones that are interesting for our study are the channels 7 to 10. And at the same time, you see the spectral response function of the Harmony panchromatic channel, which is the one given by the black continuous line. And if you also consider the sensor spectral response function, which is given by the black dashed line, the combination of the 4 channels from 7 to 10 can be thought as a proxy of the Harmony panchromatic performances. There is also one point that we have to stress, which is the location of channel number 8 at 9.7 micrometers, which is located in correspondence of a peak in optical thickness for ozone, which is then expected to particularly degrade our estimate of the thermal features at the sea surface. So we go on with some results. Here you can see the brightness temperature derived for the 10.8 micrometer channel. So here we can recognize structures that are really in agreement with the well-known oceanographic activity in this area, which is the West Mediterranean. We are in the Alboran Gyre, and here you can recognize the intrusion of cold water from the Atlantic Ocean into the Mediterranean through the Gibraltar Strait. And you can also see the gradient intensity of this, the thermal signatures of this oceanographic scene represented by the 4 different channels, with the 10.8 micrometer channel, which is the one which is more sensitive to the sea surface condition. And at the same time, you can recognize the 9.7 micrometer channel, which is affected by ozone, which is the one giving the worst estimate of the thermal features gradients at the sea surface. What happens when we compare the 10.8 micrometer gradient intensity estimate with the one given by our synthetic panchromatic channel, which is obtained averaging the radiances in the 4 IR channels and then deriving the brightness temperatures for these averaged radiances. If we compare the results along a 1D transect, which is given by this black dashed line that crosses the main fronts of the Alboran Gyre, you can see that the black line is the gradient intensity given by our synthetic panchromatic channel, and in orange you can see the one given by the 10.8 micrometer channel, which is our reference. So the gradients are correctly located, as we also saw previously with Sentinel-3 data, but again we found a smoothing of the panchromatic derived brightness temperature gradients. On average, we recover roughly 80% of the total signal. So the last point of this presentation is the way we address the optimization of the thermal gradients computation from 2D images, considering the high radiometric noise of the Harmony thermal infrared payload, considering state-of-the-art infrared emissions like sensors like SLSTR. So here you can see the difference in NEDT in the infrared channel from these 2 sensors, and the necessity to optimize the computation of the thermal features gradients at the sea surface numerically. In order to do this, we performed a very simplified analytical study in which we generate an analytical SST field, which is given by this equation emphasized in red. You can find the corresponding structure as an analytical SST here on your left. This structure can be assumed as an eddy undergoing deformation in the ocean surface, for instance. And on the right, you can see the SST gradient, which has been computed analytically via this equation. So the idea is to then intercompare the SST gradient intensity estimated with different types of estimators, going from the central differences up to more advanced numerical schemes, which are given by kernels with large number of points that are accounted for in order to compute gradients in a specific location, here indicated with payload kernels, and to intercompare the estimates of this gradient intensity in absence and in presence of noise. In absence of noise, as you can see, once again, along this 1D transect that crosses the center of this analytical eddy shape, you can recognize the analytical gradient intensity given by the black dashed line. And you see that the red line, which is the one associated to the central differences estimator, is the one that better represents the gradient intensity found in the analytical case. And the central difference scheme is the one that simply considers points left and right of a specific location in which we are interested in estimating the gradients. But very interestingly, the situation changed a lot when we start introducing radiometric noise. Here we just introduce Gaussian noise with increasingly high standard deviation. And you can see that in this case, Pavel 11 kernel, which is the one that accounts for 5 points left and right of a specific location in which we want to estimate the gradient intensity, is the one that outperforms all the other estimators and that is able to best represent the frontal areas, so the areas in which we switch from no gradient to a larger gradient intensity. Of course, using a wider stencil for computing the gradients will depend also on local cloud condition and on the distance to the coastline. So this will be taken into account. We go quickly to some conclusions and perspectives of this work. So we showed very simplified studies in which we show how we are contributing to the development of this ESA Earth Explorer 10 mission for the estimate of SST gradients at the sea surface from single-channel top-of-atmosphere observations. We mainly relied on existing data of sea surface temperature and brightness temperature from the SLSTR and Severi sensors that both show that brightness temperature can correctly locate gradients at the sea surface, although we still need to work in the future to try to recover the full intensity of SST gradients using these approaches. One last point is that we also introduced a way, a sort of guideline to compute gradients in high radiometric noise regimes. We have to say that this type of gradients that we have identified, like the wider stencil ones, like the Pavel ones, have also been used by David Wade recently to estimate gradients from the EcoStress mission with nice results in the West Mediterranean. But of course, once again, in the future, we need to take into account the presence of clouds or also the distance from the coastline for this type of application. So I thank everybody for the attention. Just to mention that the results of this presentation are summarized by a paper published early this year in 2023. So I leave you with the reference if ever you are interested in reading more about that. And one last slide of acknowledgement to Rosalia Santoleri, who supported the study since the beginning. And also to Flavio Mariani from ESA for lots of discussion on the Harmony tier payload characteristics. Thank you for the attention. That's all from my side.